Okay, this week we are using something called a force table to measure forces and then use the fact that forces are vectors and forces that cause something to be in equilibrium add up to 0 to allow us to test that vectors can be added using tip-to-tail method or by components. And we will add the vectors to the forces we're dealing with and show that they equal 0. Okay, so before we go any further, just a quick review of what vectors are. Vectors, or a vector quantity, is a quantity that has a magnitude and a direction. Right? There's a lot of these in physics. Can you give me some examples? Force. Okay, good. How about another? Displacement. Others? Yep. Force, displacement, velocity. Anything from this side of the room? Acceleration. Good. Okay, so those are all vectors. There will be other vectors that we encounter later in the semester, like momentum, angular momentum. And they're different than scalar quantities. Scalar quantities just have a magnitude, things like temperature or distance. Okay, so adding quantities that have a magnitude and a direction is a little more complicated than just adding scalar quantities, right? Because we need to add up not only the magnitudes but also the directions. So there are a couple ways we do this. One is we can take these different quantities, and if we know, for example, the force that an object exerts, we can represent that as an arrow, where the length of the arrow is proportional to the magnitude of the force. The direction of the arrow is the direction that the force is applied. And so if we have a number of forces that we want to add, we can add them as vectors. We can add their arrows using the tip-to-tail method. That's where you line up all the arrows. So the tip of one lines up with the tail of the next, and you follow around the path that they take. And from the base of the first to the tip of the last, you get the net force, or the sum of the forces. Or we can add them up by using components. That's where we take the x and y components of the vectors and then add those up mathematically. And we're going to do both of those things today. So we're going to use a force table. That's what's sitting in front of you. It kind of looks like this from the side. There's this platform with a little post in the middle, a ring around the post, some strings coming off the ring, and then some pulleys around the outside. So we will run the strings over the pulleys and attach some masses to them. The masses will pull down, or gravity will pull the masses down, producing forces. And that force pulling down, because the system's in equilibrium, means there must be a tension in the string to oppose it. And an ideal pulley only changes the direction of the string, but not the tension in it. So we have the same tension over here pulling on the ring. So by applying masses to the end of the strings and then weighing those masses, we'll know how much force is being applied to the ring by the strings. And the pulleys are on brackets that can be moved to different points on our table so that we can change the angle that the forces are applied to the ring. And so you will set up your experiment with one force pointing straight up. And by straight up, I mean pointing at 0 degrees, as marked on the scale on the perimeter of the table. And another force pointing off. The lab manual suggests you use something between 40 and 70 degrees. It's up to you what you use. And you'll apply masses to the end of those strings. And when you do, this ring that I've drawn in red is going to be pulled by the sum of these two forces up and to the right. And it'll be pulled until it contacts this black post. Right? That post is sticking up around the ring. So the ring will be pulled until it hits that. At that point, the system's in equilibrium. We've got a couple forces pulling up and to the right, and the post is going to be pulling down and to the left. We know what the forces pulling it up and to the right are because we know how much mass we've hung off. But we don't know how hard the post is pulling back, and we have no way to measure that. So what we'll do is we'll take our third string and we'll lay it out in the direction that's opposed to where these two forces are pulling. We'll wrap it over a pulley, so we may need to move that pulley over to an appropriate location. We'll hang it off the edge, and then we'll apply some more mass to that. We'll call this our balancing force. And we'll adjust the angle of this force by moving the pulley around, and we'll adjust the magnitude by adding or subtracting masses until this balancing force is just enough to balance these first two forces. And that means that we can move the ring away from the post, let go of it, and it will stay there. It won't rely on the post to hold it in place. So once we've done that, our ring is in equilibrium. Newton's second law says F equals ma. There's no acceleration, so there's no net force, which means these three forces must add up to 0. Okay, so physically, we ensure that constraint by making sure that the system's in equilibrium. And then mathematically, we'll test that the vectors that represent these three forces add up to 0. They won't, though. We will draw the vectors out, we will add them up, and we will not get 0. Why will we not get 0? There's uncertainty. Yeah, there's always uncertainty. So we need to keep track of how much uncertainty there is so we can say whether or not our measurement is close enough to 0 to be able to say it's effectively 0 given our measurement uncertainty. Okay, so what we will do is you'll fix the position and the mass for force 1 and 2. And then we'll treat it as if all the uncertainty is in this balancing force. And in order to figure out how much uncertainty there is in the magnitude of the force, what you'll do is you'll take the mass that you have hanging off the string for the balancing force, and you'll add a little bit more mass to it. And you'll keep adding mass until eventually it's pulling hard enough that it moves the whole system over and the ring hits the pulley. And then you'll take mass off, and you see how much mass you can take off before it gets pulled in the other direction and hits the post. Now, if it were an ideal system, there would only be one exact force that would cause it to balance, and any additional mass would cause the ring to slide over. And if any mass less than the exact value would slide over the other direction. But it's not a perfect system. These pulleys have friction. And so it turns out you need to pull hard enough not only to accelerate the mass, but also to overcome the friction of the pulleys. And that's the dominant source of our uncertainty. And we'll quantify it by changing the mass on the balance hook. Okay? And we'll record a range of masses over which it balances. That's going to be your uncertainty range for the magnitude. What other quantity does a vector have? Direction. So we also need an uncertainty in the direction. Okay, so we'll read off the direction of these strings using the protractor, or the scale that's around the perimeter. And then we'll take this pulley and we'll move it a few degrees to either side. And if you move it just a little bit, the ring will displace, but it won't slide into the post. When you move it far enough, the ring will slide over to one side and hit the post. And that's what we're trying to find, is how far do we have to move it over before the ring slides over and hits the post. Okay, so we'll do that in both directions. It'll be a few degrees in either direction. So record that, and that will be your uncertainty in angle. Okay, so that's the data collection. To analyze it, we're going to take our values and we're going to graph them by drawing them as vectors. Okay, so let's say force 1 we measured to be, I don't know, let's say 1 Newton at 0 degrees. Force 2 was maybe 1.5 newtons at 45 degrees. and maybe the balancing force is measured to be, say, 2.4 newtons at 100 and, let's say, 200 degrees. And let me write that with uncertainty, plus or minus 5 degrees. This is just example. I just made this up off the top of my head, but this might be similar to what you'll record. You have a value for the magnitude and direction of the first two forces, and then a magnitude and an uncertainty for the a quantity and an uncertainty for the magnitude and the direction of the balancing force. Now, we want to draw these vectors as arrows. So the first thing we need to figure out is how big should our arrows be? Okay, we want them to be proportional to the force, right? But we don't have, there's no way to draw a 1 Newton force, right? We can only draw things that have certain lengths. We can't draw an arrow that's 1 Newton long. We can draw an arrow that's a meter long or a centimeter long. So we have to choose a scale factor. Okay, so some conversion from newtons into centimeters, let's say. So we want to draw the whole thing on a piece of graph paper, which is located up front. So you can pick up a piece of graph paper to do your drawing. So you know the size of the graph paper. You want your vector diagrams to fit on that graph paper, and you don't want them super tiny that they're hard to read. So you need to think a little bit about how big your vectors should look and what would be an appropriate scale factor. So I might choose 10 centimeters per Newton. And that would tell me my first force should be drawn 10 centimeters long at 0 degrees. So if I want to add the vectors using tip to tail, I know my first vector is going to point straight up. My next vector is going to be a little longer and point to the right. And my balancing vector is going to point down like this. So I'm going to sketch out that sort of triangle. Yeah? Yeah, we're treating all the uncertainty as if it's all on the balancing vector. Okay, so we're saying we apply force 1 and force 2, and then we measured the force necessary to balance it. So all of our uncertainty will be on the balancing vector. So you want to sketch out just roughly what this diagram will look like, not on your graph paper, just in your notes, to get a sense of what scale factor will be reasonable. Right? So I chose to make this 10 centimeters. This will be like 15 centimeters. That should fit on my piece of paper. Okay, so let me draw this to scale now on my graph paper. I'm going to use my meter stick. And I'm first going to draw my first vector at 0 degrees. So I'm going to define 0 degrees as pointing straight up. I'm going to pick my origin to be in the bottom left in this case, because I know my triangle is going to go off up and to the right. And I will draw my first vector. And I'll make that 10 centimeters long, pointing at 0 degrees, meaning point straight up. Next, I want to draw force 2. It's 1.5 times as long, or 1.5 newtons times 10 centimeters per newton is 15 centimeters. And it's at 45 degrees. So I need a protractor. There are protractors available up here. I'll pass them out as you're getting started. OK, so where should I draw force 2 from? Where should I start drawing force 2? From right here, okay, from the tip of vector 1, that's where I put the tail of vector 2. And in which direction should I draw it? 45 degrees. Okay, so I'm going to use my protractor. I'm going to lay it down with the origin at the tail of my vector. And I'm just going to mark off, put a tick mark where the 45-degree angle is. And then I can line up my ruler, use that tick mark to define the angle, use the scale on the ruler to measure the appropriate length, and label that. And now I'll draw my balancing vector. Where do I draw that from? from the tip of force 2, and it's at 200 degrees. Right? So my protractor does not go up to 200 degrees. It goes 0 to 180. So how do I get 200 degrees? How do I find where 200 degrees is? So I'm measuring from straight up, right? So from straight up to straight down is 180 degrees. So I'll have to add 20 to that. So I'm measuring 20 degrees over from straight down. Okay, so I can use my protractor however I'm most comfortable to do that. And I want to draw, in this case, a 24 centimeter line. And this is what I have. Okay, this is my diagram. Where should the tip of this vector, the balancing vector, be? It should be at the beginning. If it comes back to the beginning, then the sum of these forces is 0. As it is, the sum of the forces is not 0. The sum of the forces is this quantity right there. And I'm not actually going to measure that. I'm not going to measure that sum. Instead, what I'm going to do is I'm going to include my uncertainty in this graph. Okay, so the balancing force wasn't exactly 2.4 newtons. It was 2.4 plus or minus 0.2. Okay, so this 0.2 newtons on when I convert that into centimeters, that's 2 centimeters. It means my vector could actually be 2 centimeters longer or shorter than this. Right, so use your ruler. Measure 2 centimeters shorter or 2 centimeters longer. And I get a range for the length of my vector. And the angle wasn't necessarily exactly 200 degrees. It was within 5 degrees of that. Okay, so use your protractor. I'll just make tick marks at plus or minus 5 degrees. I'll use my ruler to extend these angles. And now I've drawn a range of angles and a range of lengths. And I can combine those by drawing a little ellipse where the one axis of the ellipse is along the direction of the vector and one is perpendicular to it. One axis of the ellipse is in the direction of the vector, one is in the tangential direction. And this ellipse then represents my uncertainty. My measurement essentially says the sum of these forces is somewhere within this ellipse. Okay, so how do I know whether that agrees with theory? What should my graph look? What does my graph have to look like in order for me to say these vectors all added up to 0? John?
You said the circle has to go over the beginning point.
Yes. And does it here? No. Okay, so within my experimental uncertainty, I have measured a balancing force that does not agree with the sum of the other two forces. Okay? Now, if my ellipse were bigger, or wider in this case, if it were like this, then I could say the sum of the forces is 0 within my measurement uncertainty. Okay, so we're doing uncertainty like we have all other weeks. We're just representing it differently. We're doing it graphically rather than using formulas to calculate it or manipulate it. But you need to be able to interpret your result, just like we interpret our results every week, taking into account the uncertainty. Okay, so that's what one of your graphs should look like. We're actually going to draw two graphs, one for the tip-to-tail method and one for measuring the components. Okay, so for measuring the components, you're going to draw the exact same vectors on a separate piece of graph paper. Only difference is we're not going to arrange them tip to tail. We're just going to draw them at 3 arbitrary points. Okay, so I have F1, F2, and FB. And the reason we're going to do that is we're going to use the graph paper to determine the magnitude of those vectors, or the components of those vectors. We are not going to use our calculator. Okay, we are not using our calculators. We are not using any trigonometry today. We're going to use the graphs to show what the components are of those vectors. The reason is, it's very easy to get confused when doing trigonometry and take a cosine when you meant to take a sine, or take a sine when you meant to take a cosine. But if you use the graph, you can find the components, and if you know what you're doing, you'll get the right answer. And if you don't know what you're doing, you won't get the right answer. Whereas with the calculator, it's easy to know what you're doing and screw up, or to not know what you're doing and get lucky. Okay, so our vector 1, we want to find the x and y components of it. Well, what is the x component of vector 1? 0. It's 0. So I should put on this graph my axes so I know them. By definition, vector 1 was at 0 degrees. It was pointing straight up, so its x component is 0. And then what is its y component? I expect it to be 1 Newton. Okay, but I'm not just going to read it off from here. What I'm actually going to do is I'm going to measure it using my ruler, measure some number of centimeters, use a scale factor to convert that into a number of newtons. It should be 1 Newton, right? Because I started with 1 Newton. I scaled that into some number of centimeters. Now I'm scaling it back. For force 2, the x component is the component, if you were to illuminate this, if this vector were some opaque obstruction and there was a light directly above, it would be the length of the shadow that it cast on the ground, right? Or the projection of this vector onto the x-axis is a mathematical way of saying that. So you'll draw this component and label it as f1x. And then likewise, you'll draw the y component. And so you can either draw the y component using the same method, or you can draw it as another leg to a triangle that has a hypotenuse of f2. Okay, so either way you want to draw it is fine. But once you've drawn these two vectors on your graph paper, you can then measure their lengths. Okay, so I measure some length, and then I divide it by the scale factor to get some number of newtons. And then I do the same thing for x and for y. I'm relying on my measurement, so I may not, even though mathematically we know if this is at 45 degrees, they're going to be equal, I may not get that because there's uncertainty in my measurement. And then you do the same thing for the balancing force. So you'll draw the components, you'll label them. In this case, they're both negative, so keep track of that sign as well. And then you'll measure their lengths, divide by the scale factor, and get some number of newtons. Let's say I get that. The problem with this is I haven't accounted for uncertainty anywhere. So if I just try to add these quantities up, if I try to add up the x components, I'm not going to get 0. In order to say whether they're close enough to 0, I need to include the uncertainty. And so again, I will draw the same ellipse over here on my balancing force. And then when I take the projection of this vector, I also have to take the projection of the ellipse. Right? So if this is my x component, this distance is my uncertainty. Does that make sense? Alexandra?
Do we just measure it with a ruler, or do we use like sine?
Use a ruler. Do not use sine and cosine. No trigonometry today. Just use graphs and rulers. We're really trying to get back to basics so you can really see and visualize and work with your hands and see where these components come from and not have it some abstract thing. Okay, and we'll do the same thing for the, I guess this was the y component, not the x component. We'll do the same thing for the x component of the vector. We will take the projection of this ellipse onto the x-axis, and the width of that is twice the uncertainty. It's the center plus or minus. Okay, so you can measure with your ruler the size of that projection, use your scale factor, and that will give you a value for the uncertainty. Okay, so once you have the x and y components of all the vectors, we're trying to add these quantities up to see if they add up to 0. And so we're trying to test this equation by adding vector components. So we'll do that for x and y. So f1x plus f2x plus f3x is, now just add up the numbers, 0 newtons plus, say, 0.8 newtons plus a negative 0.81 newtons. And I get minus 0.1 newtons. Okay, I'm trying to test if this is equal to 0. But keep in mind, I have uncertainty. So is this value equal to 0 within my measurement uncertainty? It is. I measured minus 0.1 newtons with an uncertainty of minus 0.2 newtons. Okay, so if the uncertainty is bigger than our difference from 0, then that essentially adds up to 0. And we'll do the same thing for y. Adding up the y components and testing if they're equal to 0. Your uncertainty in x and y may not be the same. And in this case, if I look at my value over here, when I added up the y components of these three vectors, was my result equal to 0 within my measurement uncertainty? No, it wasn't. So, given that the x components add to 0, but the y components don't, what can I conclude about my vector addition? Was I able to add the vectors and get 0? No. We need both components of the vectors, or we need both the magnitude and the angle to agree in order to say that we've measured what we expected. So that's the experiment. Any questions? Are you using your calculator today with cosines and sines, trigonometry? No. No, you're not. Okay, John? How do you find it when you're doing it by components?
With 5 degrees
The exact same way. This vector and the ellipse here is drawn exactly the same way it's drawn over here. Okay, so if you have a 5-degree uncertainty in angle, you draw lines that are 5 degrees less than or greater than your main measurement. And with the length, you draw tick marks that are plus and minus the uncertainty in length, and then you just draw an ellipse that fits right between those two angular limits and between those two magnitude limits. Okay, go ahead and get started. Graph paper's up here. I'll just put the protractors with the